Welcome, everyone. Warm welcome. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. Anything you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 2000 AP Calculus exam. This appeared on the AB and the BC exam. In the year 2000, beginning of the millennium, 20 years ago, 25 really. Okay, here we have a typical problem with differential equations in the context of derivatives. So we're going to be doing this process of implicit differentiation. Very straightforward, accessible from AB as well as the BC students. So go ahead and give yourself about, let's say 12 minutes to work on this on your own. And then when you're ready to check how you did, you can come back and see where we rack up some points along the way. Okay, let's get started. So we're given a curve, not a function, but a curve, which is mapped out by the following equation: xy squared minus x cubed y equals 6. They want us to first show, emphasis on the show that dy dx is 3x squared y minus y squared over 2xy minus x cubed. Okay, so this is fairly easy to do. We just need to be aware that when we take a derivative of both sides of this equation, we're going to want to use the product rule. Okay, and we're going to use the product rule in a couple places because there are two products. Of course, the right side of the equation is simple. The derivative of 6 is just 0. The really interesting stuff is happening here. So we have x times y squared, the derivative of which is going to be the derivative of the first thing times the second thing, plus the first thing by itself times the derivative of the second thing. And we have that twice. We have two product rules. So we're going to be doing that twice. We're going to put a minus because this is also a product. X cubed times y. So let's go ahead and put these into place. We have 1, of course, and y squared. Now, whenever we take a derivative of y stuff, we're going to use the chain rule. So we're going to have 2y, which would be like the normal, let me move this a little bit, which would be the normal derivative of something like x squared. But then we're going to multiply this by dy dx because of the chain rule. Now this minus is referring to the next product rule. So we're not focusing on xy squared anymore, we're focusing on x cubed y. So here we have 3x squared times y plus x cubed dy dx. Yeah. Okay, and while you're solving this for dy dx, while you're isolating, you're going to want to be aware of which terms have a dy dx in it. That would be this one and this one. So let's separate those terms. We have dy dx, and that's going to belong to the 2xy, but it's also going to belong to this negative x cubed. Anything without dy dx is going to get moved to the other side. So y squared is going to get moved to the other side. It's going to be subtracted on the other side. Whereas this negative 3x squared y is going to be added on the other side. We're getting rid of it from the left side of the equation, and that's because we want dy dx by itself. And of course, we can solve dy dx by just dividing this parenthetical expression, 2xy minus x cubed. I'm pretty sure that's around what they wanted us to show. Yep. See, they wanted us to show that this is what dy dx is equal to. So we've successfully found an equation which gives us the slope of the tangent line at any point. Let's move on to part B. Find all points on the curve whose x-coordinate is 1 and write an equation for tangent line at each of these points. So, two parts to this. We have to find some points where the x-coordinate is 1. What exactly does that mean for us to do if they tell us the x-coordinate is 1? It means we need to plug in x. Where do we need to plug it into? Well, we need a y value because we need points. But we also need slopes because we need the equation of tangent line, which requires us to have the point and the slope. And it's suggesting that there may be more than one point. So we have to find our points first, and the way we do that is we plug it into the original equation. So let's take the original equation and plug in x equals 1. Pretty well-behaved equation, because 1 cubed is still just 1, and 1 times y squared is just y squared. This equals 6. Now we're going to solve for y. This is a basic quadratic equation. It factors very nicely. So go ahead and factor that. And this will reveal that we have 2 y values. We're going to have y equals 3, and we're going to have y equals negative 2. So that means we're going to have one equation which reads y minus 3 equals some slope times x minus 1. And then we're going to have another equation which reads y minus negative 2 equals some slope times x minus 1. We have to find what these slopes are, and we can use the derivative for that. So we can say at 1, 3, the slope m, or dy dx, is equal to 3 times 1 times 3 minus 3 squared. So that's a 0. Let's make sure the denominator is not also 0. 2 times 1 times 3, which is 6, minus 2 cubed. So the slope at the point 1, 3 is 0. Okay, well that makes the line equation pretty easy. That's just going to reduce to be y equals 3. That's the equation of that line. Now in the case of 1, negative 2, let's plug that in. Dy dx equals to 3 times 1 times negative 2 minus, careful, negative 2 squared, which becomes a positive 4, but we are still subtracting it, over 2 times 1 times negative 2 minus, oops, I think I didn't plug the x in correctly over here. That should have been minus 1. Still ends up being 0, but I just wanted to clarify that mistake. Negative 4 minus 1. So this becomes negative 10 over negative 5, which is a slope of positive 2. And now we can write our equation of tangent line with that slope. So y plus 2 equals 2 parentheses x minus 1. I'm totally fine with you leaving it as that. Generally, they don't require you to put this into slope-intercept form on the AP exam. Now, last part. Let's take a look at part C. It wants us to find the x-coordinates of each point. Again, they're suggesting there's more than one point on the curve where the tangent line is vertical. This gives us all of the clue how to start. This tells us that dy dx is going to something over 0. So let's find out what would make the denominator of the derivative 0. Well, that means that the 2xy minus x cubed part is equal to 0. Okay, each point on the curve. Well, if we want to put y in terms of x, that could be rather helpful. So let's sort of like solve for y. Which means that y is simply equal to x squared over 2 or 1/2 x squared. Now, if we use this describes the relationship between x and y, which will guarantee that the denominator of the derivative is 0. Now, we don't know which points that is, so we have to plug this into the original equation. Let's go ahead and plug that into the original equation. So we have x times y squared minus x cubed times y equals 6. This is going to become x times 1/2 x squared minus x cubed times 1/2 x squared equals to 6. So we're going to have 1/4 x to the 5th minus 1/2 x to the 5th equals to 6, which gives us negative 1/4 x to the 5th equals to 6. Multiply this by negative 4 on both sides, and we get x to the 5th equals negative 24, which means x equals the 5th root of negative 24. Very interesting. Okay. There is the x-coordinate. Now, I don't see 2 points here. That's kind of what I was a little bit concerned about. I don't detect 2 different x-coordinates. So if I had to guess, I would say that is the x-coordinate. Let's see if anything else would work. There has to be a reason why they put each. Let's look at what the y value would be. Maybe there are 2 y values that result from, the same y value that results from different x values. Got it. So I think what I can say is that if x equals the 5th root of negative 24, or if x equals negative the 5th root of negative 24. There we go. Because either way, when I square that, in other words, when I plug that into the derivative, to dy dx, the denominator will be 0, which means the tangent line will be vertical. Okay, great. So that does it for this problem. Part C was a bit tricky at the end of there with the concept of how to determine whether or not there's 1 point or 2. Other than that, very standard implicit differentiation problem. Every time you see equation of the tangent line, I want you to get in the habit of writing y minus y value equals m times x minus x value. You can possibly get a point for that. Nothing else particularly tricky other than the tediousness of isolating dy dx, but that's really just like an Algebra 1 skill that's been made a little bit tougher here. Alright, that should be enough blab out of me, you A, B, and BC students. I'll see you guys next time in the void.